Alright, so I want to talk about how we handle momentum in two dimensions. Um, and let's just look at a graphical representation first. Let's say we have a ball that's coming into a table with a momentum PO. It bounces off the table at an angle and leaves with a momentum PF. What direction has the impulse been there? Well, we have to find this using vector math. So if we just do it using our arrows, I think it's pretty easy to see what direction the impulse is in. We have PO going down and to the right. The opposite of PO, negative PO, would be parallel to PO, but going in the other direction. So if we wanted to do PF minus PO, we reverse PO, and then we add PO, negative PO and POF head to tail. So there's PF, there's minus PO. When we draw the resultant vector from the tail of PF to the head of negative PO, we see that the change in momentum, delta P, is up. So, not surprisingly, when you have something going down and right, and then later it's going up and right, the right part hasn't changed, just the up part did. And that's what this picture is showing us. Now, it'd be nice if we could do this numerically, and we do this in a similar way we did forces. We find the part of a momentum vector that's x, we find the part of the momentum vector that's y, we deal with them separately. So let's look at a problem. So in this problem we have two billiard balls colliding on the table, the 4-ball and the 9-ball. They start with 9-ball at rest, 4-ball has horizontal velocity. There's a collision which sends the 9-ball up and to the right and the 4-ball down and to the left. So how do we deal with that? Well, just like we did with forces. What happens in x, what happens in y stays in y. We have one momentum problem for x, we have one for y. Notice there were two balls before and two after. So we have a term for each ball before and after. And we have that for x and for y. Notice the labeling here. We have M1 V10, M2 V20, M1 V1F, M2 V2F. We have the same in both x and y, but I put a little x on the x components and a little y on the y components. So how do you do it? Well, you take our non-x or y velocity, which is ball 1 at the end, and you use trig to break down its components, so V1Fx, V1Fy. So did a little triangle, cosine got me x, sine got me y. Basically, you solve each of these problems separately. Here I'm solving for V2 final in the x. Here I'm solving for V2 final in the y. And then, once you have those, you just add them back together. So the way you find out what V2 is you just do the Pythagorean theorem. A squared plus b squared equals c squared. And that gets you the hypotenuse and the magnitude of the final vector. So 3.73. And then to get the angle, since you know the sides of the triangle, you just do inverse tangent, and that gets you the angle. So, all in all, a two-dimensional momentum problem is just two one-dimensional momentum problems. You solve for x, you solve for y. You figure out what the components of the vector you want are in x and y, and then you add them back together.